Welcome here, everybody. This is day 4 of CPR, and as we discussed yesterday, we're going to talk about the vector nature of momentum. Today we're going to do an example problem. And before I go any further, I should say that today's episode is brought to you by the Greek letter alpha. Looks like a fish with a bite out of its tail. Remember, some radioactive substances, they give off alpha particles, which are basically just helium nucleuses. Anyway, the example we're going to look at is on your vector nature of momentum assignment. It is right near the top of the page and it is labeled. And of course, the first step in any problem is get the information you're given in the question on your page in the form of a diagram. And in purple, that's what I have here. And let's just see what kind of a job I did. The question says a 2,000 kilogram car is traveling east at 24 meters per second, enters an icy intersection and collides with a 3,600 kilogram truck traveling south at 10 meters per second. If they become coupled together in the collision, what is their velocity immediately after impact? So the collision takes place right there. There they are coupled together, and we want to figure out what velocity they have, how fast they're going, and in what direction they're moving after the collision takes place. And you figure if one's going this way and the other's going this way, when they collide and stick together, they're going to move off in this kind of direction. And just before we go any further, we should talk a little bit about the significance that this is an icy intersection. Now, an icy intersection, it's bad news for the drivers, but for us analyzing the situation, it's actually pretty fortunate. Because it's icy, that means when they slam on their brakes and their wheels lock up, there's going to be minimal friction. So that's an outside force that we don't have to worry about. Also, gravity is an outside force, but it's being counteracted by the normal force of the road. So that's another outside force that we don't have to worry about. You have to remember that outside forces, they screw up the law of conservation of momentum. What we have here, of course, when these things collide, you're going to have one part of this system exerting a force on the other part of the system, and vice versa. You know, one part of the system exerting a force on the other part of the system. Those are internal forces, though, and they do not screw up the law of conservation of momentum. All right, let's see if we can do this now. Now, take a look at what you have. You got a bunch of masses. You got a bunch of velocities. Well, mass and velocities, they scream momentum. You have a collision taking place. Whenever you have a collision taking place, things coming together, or an explosion, things getting blown apart, think law of conservation of momentum. The total momentum of everything before is going to equal the total momentum of everything after. So I write that down over here. The total momentum of everything before is going to equal the total momentum of everything after. And of course, the total momentum of everything before is going to be the momentum of the car, okay, plus the momentum of the truck. Now, let's figure out what the momentum of the car is. Okay, that's something we can do. Why not? The momentum of the car, easy enough. The mass of the car times its velocity. So the momentum of the car, its mass times its velocity. There it is, 48,000 kilogram meters per second, straight east. What's the momentum of the truck? Well, that's going to be its mass times its velocity. 3,600 times 10, 36,000 kilogram meters per second, straight south. Remember, of course, that the directions of the momentums are the same as the directions of the velocities. Okay. Now, if we want to figure out the total momentum of everything before the collision, we got to add these two things together. we got to add these two things together. And of course, you can't do that arithmetically. They're vectors. They're making weird angles with each other. One is going south, one is going east. So we got to add these things. We got to do this addition on a vector diagram. So let's draw the vector diagram. Now it's going to be a right triangle, so we don't have to worry about any scaled diagram. Here's my vector diagram right here. First I put down the momentum of the car, 48,000 kilogram meters per second, straight east. Then I add on to that the momentum of the truck. So I pick it up, plop it down, tip the tail like that, 36,000 kilogram meters per second, straight south. And my resultant, my answer, what I'm looking for, the total momentum of everything before the collision, there it is, from where I start to where I finish. And you can figure that out using Pythagoras, or you might notice that this is actually a 3, 4, 5 triangle. This is a 3 side. 3 times 12,000 is 36,000. This is the 4 side. 4 times 12,000 is 48,000. So this is the 5 side. 5 times 12,000, there's our answer. 60,000 kilogram meters per second. And of course, we need a direction. So let's figure out what this angle is. We can do that. It's just a little bit of trig. Take the inverse tangent of the opposite over the adjacent, and that angle comes out to be 37 degrees. So the total momentum of everything before, there it is right there. 60,000 kilogram meters per second. 37 degrees south of east. Okay now, we're very, very close to figuring out this velocity. How can I possibly figure out this velocity? Okay. Well, you got to remember, the total momentum of everything after is equal to the total momentum of everything before, which is 60,000 kilogram meters per second down at that angle. So yeah, the total momentum of everything after is going to equal 60,000 kilogram meters per second down at an angle of 37 degrees. How do you figure out the total momentum of everything after? Well, you take the mass times the velocity. So let's do that right now. The total momentum of everything after is going to be the mass of these two things combined together. 2,000 plus 3,600 is going to be 5,600. You multiply the mass times the velocity, which is what we're looking for. V prime, that means the velocity after the collision, and that's equal to 60,000. So you just solve this equation. Bring the 5,600 over to the other side. And that works out to 10.7 meters per second. And of course, the direction of this velocity is going to be the same as the direction of this thing's momentum, which is 37 degrees down from straight east. So we use compass directions in the question, right? So let's give compass directions back on our final answer. What's the direction of my final velocity? Same as the direction of my final momentum. That's going to be what? East, and then 37 degrees down towards the south. Done. And you'll notice that I did not talk about impulse or change of momentum at all in here. That's a common mistake that people make when you're just doing a question like this and you're dealing with law of conservation of momentum. Don't worry about impulse or change of momentum. Just worry about everything's momentum. And yeah, as far as the vector nature concerns, nothing has really changed. It's just like before, except when you have to add a couple momentums together, well, now you might have to do it on a vector diagram. So as far as your assignment is concerned, you can now do this one, the one called the vector nature of momentum. You should do questions 1, 2, 3, and 5. Yeah, let's go with that. Questions 1, 2, 3, and 5. And you'll notice there's no solutions given, there's only answers. And that's because the best way to learn this stuff is just struggle through it and try it on your own. Not to worry though, I will post solutions to these questions, likely in the form of a PDF sometime tomorrow. So anyway, good luck with this, and we will see you again fairly shortly. Bye for now.